This video is about parallel circuits. It will be very similar to what we saw in the previous lesson, which was series circuits. The equations will look quite similar, but there's a subtle difference. I think the number one thing to recall would be that in a series circuit, the current is the same throughout that circuit. A parallel circuit, however, the current is different throughout the circuit, and the voltage is this thing that stays the same. So those are your two facts to memorize. In a series circuit, current is the same. In a parallel circuit, voltage is the same. We'll start with that definition. Parallel wiring is when the elements of a circuit are connected so that they have the same voltage. Parallel wiring is when the elements of a circuit are connected so that they have the same voltage. I'm going to add here that in parentheses, I'm going to add they are situated between two junctions. By that I mean the wire splits. Those two elements are on their separate parts of the wire, and then the wire rejoins. The split in the wire and the rejoining of the wire are each called a junction. So we'll look at 4 pictures here. I'm going to draw like this. I'll have 4 pictures, some of which are parallel, some of which are not. So here we go. Here's our first example. Long line, short line is a battery. We'll have a wire come out like this. And then there's my junction. My first element is a resistor here, and we'll have a similar resistor on the other side. This is a parallel situation. These are in parallel because they have the same voltage. Now that's hard to see, but say this is a 9-volt battery. The voltage is going to be 9 volts, 9 volts, 9 volts, 9 volts, 9 volts, 9 volts. There's no reason for the voltage to drop until we get to a resistor. So it's still 9 volts, 9 volts, 9 volts, and then the voltage will drop. On the bottom of the battery, it's 0 volts, so it's 0 volts, 0 volts, 0 volts, 0 volts, and it'll be 0 all the way up to here. So both of these would cause a drop of 9 volts. That's hard to see conceptually, the whole voltage aspect of it. So the other way to just think about this is that you have the wire, it splits into 2 separate wires, and then it rejoins. So to find out if it's parallel, look to see if it splits, has the elements, and then rejoins. Here's another example. This word parallel makes people think that they have to be parallel lines like this, like in geometry, but that's not quite true. I'll show another example where they don't have this geometric parallel in them. Parallel has nothing to do with parallel lines in this case. So this one's tougher to draw because it's not really a natural way to do it. There's my first, and I'm going to go above like this. Oops, I was supposed to put my resistor right there. That squiggly line, I'm not crossing anything out. That's my resistor. I guess I could label them. No, I won't label them. I'll leave letters as they are. So here's our resistor. Here's our resistor. Notice that they're not parallel like this. They're not geometrically parallel, but the same situation holds true. 9 volts here, 0 volts here. They're both causing a drop of 9 volts. There's our characteristic junction. They're each on their own wire, and then they rejoin over here. So they are situated between two junctions, just like this is situated between two junctions. So those are indeed in parallel. We'll see one more. 2 more, actually. This one will be weird. I'm going to start with, in order to get the shape right, I'm going to draw like this. Okay. So I'm sort of starting with my junctions. There's the junction, there's the junction. Here's the battery in the middle. And my resistors will be on the outside. So these are indeed in parallel. Your charges would come out here. They would separate. There's where they separate. There's one element on each wire, and then they rejoin. Notice that there's only one element on each one, so the voltage will drop by the same amount on each of those. The last one, we'll see our first that is not in parallel. I guess it's like kind of in parallel. We'll kind of make it similar, somewhat similar to that first one. This one will have 3. Now it's possible for 3. It's possible to have 3 resistors in parallel, but they would each need to be on their own wire. What we're going to see here is I've got a resistor there. It continues. I've got a third resistor here. All right, I'm going to label these actually this time to make it clear. They are not in parallel, or you could say partially in parallel, because of that third one on there. The voltage will drop somewhat on number 2, then it'll drop more on number 3. So although these two will add up to the voltage of number 1, they're not equivalent. So this is a pretty rare case. Mostly what you should look for is a junction, one wire on each, and then a rejoin. This is in contrast to what we saw with series circuits. I'm going to sketch one real quick. It's pretty obvious whether it's like, all we really need to do in this class is figure out if it's series or parallel. This is quite obviously series because they're on one loop. For parallel, it's a split of some kind like this, blah, blah, blah. So it's pretty obvious. Usually just parallel are the complicated ones. In series, it's a continuous loop. That's all you really need to know for this class. Differentiate between series and parallel. Here's the equations. So once you figure out if it's series or parallel, you'll activate a certain set of equations. Here, by definition, if it's a parallel circuit, it's going to have the same voltage. All the resistors will have the same voltage. So the total voltage, or the battery voltage, is equivalent to the voltage of number 1, which is equivalent to the voltage of number 2, which is equivalent to all the other voltages in the circuit. Going further, the way the current is going to work here is that the currents are additive. I think the best example is this one here. You've got current coming out of the front of the battery. The current will split into 2 pieces, but that current is conserved. So maybe we'll have 2 amps on this side, 1 amp, I'm going to move my finger, 2 amps on this side, 1 amp on this side. That means that there's 3 coming out of the battery total. There's 2 amps here, 3 amps here. That must mean that there's 3 amps going into this, and thus 3 amps coming out of there. Long story short, total current is equal to all of the individual currents added up. Finally, the resistance equation. We saw in the series circuit that total resistance is calculated by adding up the other resistances. Unfortunately for parallel, that is not the case. Parallel circuits have a complicated way to calculate the resistance. That'll be one of our challenges today. So here is the equation that links the resistances in a parallel circuit. The reciprocal of RT is equal to the reciprocal of R1 plus the reciprocal of R2, and so on and so forth. 1 over RT equals 1 over R1 plus 1 over R2 plus ... Note that, same from last time, totals, VT, IT, and RT, they're also called the battery, VIR, and they're called the equivalent, VIR. So this can be V total, V battery, V equivalent, I total, I battery, I equivalent, R total, R equivalent, and I don't think R battery really makes much sense. The batteries don't have resistance. So that's why total is sometimes interchanged with equivalent. And so is battery. We'll see one example and maybe a more theoretical example if there's time. Especially when you're calculating resistance, these tend to be a little longer with parallel. It's still pretty easy, I think. The algebra overall, still looking at some freshman algebra with these. Lego. I'm going to draw a picture below this, so there will be no numbers in this prompt. It'll just be words, and then we'll put the numbers in the picture. Here we go. Please write it down, though. Calculate A. The equivalent resistance in the circuit. B, the total current supplied by the battery, and C, the current supplied to each speaker. Well, I'm just going to write resistor because I'm not drawing like a speaker system. Speakers are a very common form of resistor. This is a calculation that apparently they're using like a home stereo. But the same numbers would apply if you were doing like live sound at a big concert or something. Each speaker producing sound acts like a resistor, so you got to wire them up with the right amount of power so that they don't blow out, and so that they're loud enough. So here is the drawing. It's going to be, I'm using this here. This is the shape of it. So let's see if we can make it nice and large. Please draw this picture as well in your notes. I should have gone a little larger here, but that's all right. We have a 6-volt power source, a 4-ohm speaker, and an 8-ohm speaker or resistor. I'll also label these just to keep it a little simple. In general, you're going to want to label these. There's 1 and 2, and sometimes people put the total over there by the battery, but conceptually it sometimes doesn't make that much sense. So here we go. Let's see if we got everything then. So the first thing to do here, hope I didn't send you off with all these pictures. The first thing to do is just identify if it's series or parallel. Remember, series is just when there's no splits in the wire. If there's no splits in the wire, it's series. If there are splits in the wire, there's going to be some sort of parallel there. Even this one, I know I said it's not in parallel, but if you were to merge these two, all of a sudden it is in parallel. So I was just trying to give an odd example. We won't see complex circuits like that for a while. So here we have 2 resistors that are in parallel. So if I go to calculate the equivalent resistance like they're asking us in A, I'm going to use the equation associated with parallel circuits. Back in lesson 6.4, it was RT equals R1 plus R2. That's for a series circuit. To calculate RT here, you might be tempted to solve symbolically. That's fine. If you have the math algebra strength to calculate symbolically, go for it. I'm just going to plug in the numbers first. I think it makes it a little easier. It's kind of sloppy. I think a mathematician might lose their head watching this, but I try to pick simple numbers for the resistances to keep it simple. So you can get the least common denominator, or you can get the same denominator here. You can add these fractions if you want, but in physics, generally we don't use fractions that much, especially with real life like engineering concepts like this. So what you could do is just add them in your calculator, or you could turn them into decimals and add them. But basically what I'm saying is we're looking for a decimal. So if I take 1 over 4 plus 1 over 8 in my calculator, I'll get the following. 0.375. All of a sudden, it's real simple. We cross multiply, we divide both sides by 0.375. Feel free to show those steps if you want to get the practice, but you'll end up getting 2.67 ohms. So that is our answer. RT equals 2.67 ohms. Even if you do find this as a fraction, please convert it to a decimal. Decimals are preferred in engineering applications like this. If I make never mind. Let's just keep moving. All right, part B. Calculate the total current supplied by the battery. Let's see if we can apply Ohm's law here. I'm going to try to save space. Yeah, I could probably write it here. So we're looking for total current. I'm tempted by this because, look, I have the voltage of the battery. So if I have the resistance of the battery, all of a sudden I have the current. And look, that's what we just found. This is the equivalent resistance of the circuit. So this is the resistance that the battery is up against. Working together, these 2 resistors actually have a diminished resistance. This one has a resistance of 8, this one has a resistance of 4, but when they're wired up like this, they only have a resistance of 2.67. So they're working together and it reduces their resistance, which is an interesting effect in parallel. So the 6-volt battery is pushing that 6 volts against this amount of resistance. So I can use those numbers in this equation. Vt equals It RT. Basically divide both sides by RT. So I equals V over R. So it's 6 over 2.67. And there's our current, 2.25. Not too exciting there. I think the lesson to learn is just to keep your information separate. Note that the battery is always the total. Like there's total voltage, there's total resistance. So these two can be paired up and used in Ohm's law. Part C, calculate the currents applied to each resistor. Once again, we'll use Ohm's law. Might not be clear right away, but you'll see why. And then hopefully a bit of grab from that in the future. If we look at the equation we just used, so I'm just going to write it in the form of resistor 1. So instead of IT equals VT over RT, I'm writing I1 equals V1 over R1. You might see that, you might think that we have a problem here. I'm trying to calculate I1. I don't have the voltage. I don't have voltage 1. But actually, I do. This here, this 6 volts, is actually the voltage for the whole circuit. Like we wrote down in the last page, they have the same voltage on a parallel wiring. So by identifying this as a parallel circuit, we can see that the voltage is going to be the same everywhere. So not only is this VT, it's also V1 and V2. That's why it's important to memorize that in a parallel circuit, voltage is the same everywhere, because then you could plug that in for everything. So I1 equals 6 over 4. That's resistor 1. 6 volts. That'll get us an answer of 1.5A. And I2 is going to be the same dealy. I2 equals VT over R, V2 over R2. So I2 equals 6 over 8. Oop, I think I wrote down the wrong number. It'll be 0.75. So notice, like I said before, current is conserved. We have 2.25 amps coming out of the battery. It splits up and goes into these two. These add up to 2.25, and that is further confirmed with our equations. Ooh, I'm not showing the answer there. 2.2. That's further confirmed with this equation here, IT equals I1 plus I2. Okay. Long story short, guys, I know that's a lot of math at once, but here's what you got to take away from it. Okay, first of all, parallel circuits have a split in the wire. Series circuits are a continuous loop. And the other thing to know is what values are constant throughout these things. In a series circuit, current is the same everywhere. In a parallel circuit, voltage is the same everywhere. We'll get more practice with this in class. If you have questions before then, let me know. Thanks again for watching the whole thing, and keep up the good work.